On what I've shown on the right side is in fact the time traces recorded at this location. And what is very interesting here is that if you do that, you see that this is perfectly periodic in time. Even so, it's evolving in space. At one location, you have a signal which is perfectly periodic in time. So we can do the same for an higher frequency. And for higher frequency, what is really remarkable is the fact that you have an interplay between the first wave train and the modulation. Sorry. And due to these modulations, you get the onset of a secondary crest, which evolves. And then you have some kind of phase locking appearing here, and then a modulation of the final wave train. And we cover that very nicely with the experiments. And you see here, something which is very nice here, that you see that the whole wave train is just modulated in space. So you can see the envelope here. And that the onset of the second crest corresponds simply to the effect of the modulation, the spatial modulation of the wave train. So if we record at one place, you can see again that the signal is perfectly periodic in time. So we were able to reproduce that feature very nicely. And I will propose now a description about the instability mechanism, which is different from the instability mechanisms that were proposed by 2 days ago by Anudab Roy. He cited a series of papers about the instability mechanism of film. And here, this is another view of the instability mechanism, in view of Witten. So it is called Witten wave hierarchy. So the idea is the following. If we linearize our system of equations, they start with the capillary models, which is very simple. We get this equation for the perturbation of the film thickness, and you can see that these two parts of this evolution equation, one corresponding to kinematic waves, this is this part, and the second one corresponding, which is in fact corresponds to two different waves, which are called dynamic waves. So they are promoted by the Reynolds number. So the kinetic waves here travel at a speed which is 3 times the average speed of the flow, very fast. So why 3 times? When cosine beta is equal to 0. That's a good point. When this appears, in fact, you get still dynamic waves because this term goes to 0, but you cannot interpret them as gravity waves. Otherwise, it just corresponds more or less to gravity waves that are just affected by the flow. It is, you will see. You will see. So the system is stable if we have this portrait in time and space. The idea is the following: at long time within the Witten wave hierarchy, what dominates the flow, and that can be shown, is the dynamic kinematic wave. At small time, it should be the dynamic waves. So if you create a stable wave packet by a perturbation, at initial times the wave packet is dominated by dynamic waves, so that at later times dynamic waves should correspond to the edges of the wave packet, and the kinematic waves should be in the middle of the wave packet. So the stability conditions tells you that kinematic waves should travel at a speed which is in between the speed of the dynamic waves. This is the Witten condition of stability. However, if we plot the kinematic waves or dynamic waves, we get these shapes. So if the full number becomes quite large, what happens is that the kinetic waves can travel faster than the dynamic waves. That promotes instability. And the reason why the kinetic waves can travel faster than the dynamic waves is basically because the kinetic waves travel 3 times faster than the average velocity of the flow. This is the main reason. And it could be, this is a way to understand the mechanism. And the fact that, in fact, the kinetic waves travel 3 times much faster than dynamic waves, so they are traveling much faster than the average velocity of the flow, in fact, is a consequence of the parabola. In fact, due to the parabola, which is quadratic, in fact, the kinetic waves travel approximately to 2 times the velocity at the free surface. And the velocity at the free surface, in fact, is equal to 1.5 times the average velocity. So we get 2 times 1.5. So it gets, so the fact, so this was observed by Séverine Millet. So it's really due to the parabolic shape. It's a consequence of the velocity distribution. Okay, so if we do that with the simplified models, we get this portrait for the Witten hierarchy. So we get one dispersion relation for the kinetic waves, another one for the dynamic waves. And you see that, in fact, kinetic waves are affected by the viscous diffusion terms. Instead, dynamic waves are affected by surface tension. So if we plot the if we compute the dynamic, the dispersion relationship, you see that in fact the velocity of kinetic waves rise this way. So you have a dispersive effect of viscous diffusion onto the kinetic waves, and you have also a dispersive effect of surface tension on the surface tension only onto the dynamic waves. So if we plot the two, you can't see much, sorry about that. You can see that the velocity of the kinetic wave decreases with surface tension, which is with viscosity, which is stabilizing, and the velocity of the dynamic wave increases with surface tension, which is also stabilizing. So you can see, you can understand this way the stabilizing effect of viscosity on surface tension onto the waves. Now, if we consider convective stability analysis, so just as a reminder, convective stability analysis, you consider the fate of local perturbations, and then you look at the growth of the wave packet created by this local perturbation. Also, there is two situations. One, if you stand at one location, then if you create a localized perturbation, the localized perturbation is convected, so that the signal is lost after some time, so that you don't regularly seed the inlet of the flow with some noise. You will lose the signal. That means that the system behaves as an amplifier. Instead, when it is absolute, you just put an initial perturbation that will set a wave packet, and the wave packet invades the whole domain. So that after you trigger a global mode, you have an oscillatory behavior. Okay. So in terms of study, what you do, you write your dispersion relation, and you look at the asymptotic response at long time. So the asymptotic response is given by the group velocity, dw over dk. And to find the group velocity, you can also find the solution of this equation plus the solution of the derivatives of d respect to k. When the two are equal to 0 for a given v velocity, you find in fact the frequency, of the absolute instability mode. So these conditions correspond to the pitching of the branches, the spatial branches K in the K plane. So you do that in fact numerically. And here I compare the results from the linear solutions of the Navier-Stokes equations, which are the Sommerfeld equation. You have the K branches here in red, and I compare them to the model in blue. So this is a solution from the full second order model. And you can see that you have a pretty good agreement in terms of the branches, some deviations, but it's very, very accurate. Even so, the Reynolds number here is very large. It's 133. And if you do that, you look for the pinching point as a function of the ray velocity. You find, in fact, the response for each velocity of the maximum the maximally amplified signal, and then you find you can compare between the model and the Sommerfeld and get a very, very good agreement. Also, for these branches, because at some point you can have 2 branches of solutions. So we switch from 5 minutes, okay, thank you. You switch from one branch of solutions to another branch of solution, and this is well covered by the model. For the simplified model, you have something which is less accurate, but it works still pretty well, except for maybe the largest value of the Reynolds number here, where in fact for some because the model is too simple, you don't have this interplay between 2 saddle sorry? Okay, sorry. What I would say is that you don't cover this change of saddle points that you observe with our sum-alpha solution in that case. Okay. Okay, so we got 5 minutes. I just want to compare the method I've used with the method that have been introduced by long ago also by H.G. Roberts, which is the center manifold analysis. So the center manifold analysis is just you take the theorem for the center manifold and you try to apply that to the film problem. So the problem here is that we have already applied it and we found surface equations, because basically there is only one eigenvalue which is equal to 0. So the idea is to bring another problem which is very close by displacing one eigenvalue, so that you have 2 eigenvalues which are equal to 0. So that's the idea then that he has done, is to perturb the initial set of equations by some additional terms in red here, so that one relaxation mode have an eigenvalue equal to 0. And you have then an additional parameter gamma. When gamma is equal to 0, this is the modified problem. And when gamma is equal to 1, we recover the initial equations. So that what he did is he applied the center manifold techniques to this problem, and then performed an expansion with respect to 2 parameters, gamma and epsilon. So this is very, very difficult to do, because you have 2 expansions to do, and then the algebra is very involved. And at the end of the day, he found something which is very similar to what I've obtained, but with supplementary terms. And these supplementary terms here are quite important, because if you give that term into this model, what you see is that you cannot capture correctly the wave speed and wave amplitude at large Reynolds number. So what did in fact Roberts? Sorry, he neglected those terms. When you do that, it works very well. However, there is a problem. The problem is that those terms are necessary to obtain consistency, because it's an order epsilon, so that the threshold of instability is not recovered correctly. So you have something which is quite difficult to use, and also it has some difficulties, but still it's very interesting. And you can do the same very easily by the weighted residual technique. In fact, by introducing the following algebras. So you have the Nusselt flow. You can perturb the Nusselt flow this way. You can always do that because Q minus H cube over S3 is the order epsilon. So you say that you introduce the deviations of the variable Q with respect to the Nusselt flow value. And this is always of order epsilon as long as F verifies this constraint. Also, the idea is to say, okay, let's do as Roberts did, so that we will project, in fact, onto the first relaxation mode, which is sinusoidal. And by using the weighted residual technique, directly you get, with a very less algebra, an equation which is very, very close to what was found by Roberts with a very difficult algebra. In particular, we get the pi square divided by 12 here, which corresponds to the eigenvalue of the extraction mode. However, we have the same problem here. We have this redundant terms. On these redundant terms, principally this one, even though they have very small coefficients, modify strongly the behavior of the solitary waves at large Reynolds number. Okay, so I would like to stop here by saying that I've tried to review the different mathematical techniques that are used for modeling this flow. And I would like to thank you for your attention. The difference is that there is a double expansion. So in truth, what he found is a central manifold corresponding to this modified problem. So it's not exactly the same than the center manifold of the initial problem, because the center manifold of the initial problem is simply the Benny type equations, the surface equations, because you have only one eigenvalue which is equal to 0.
That does this.
Yes. So it's a trick to get some a model, but in fact, to say it is a center manifold of the initial problem is not true. The trick is to say I can put f, whatever function which verifies simply the boundary conditions as f. Simply because in fact here, this is already for the upside. So this perturbation, I can make a choice. So I made the choice of the first relaxation mode. So this corresponds exactly, this formula corresponds exactly to what obtained Roberts. In fact, if you don't take into account inertial terms, you get exactly this.
Long live India and France friendship.